Hello everyone, welcome to all of you in my lecture today. So here in this lecture, I am going to discuss about the non-isothermal reactor design. So in this lecture, I will be discussing about the design of plug flow reactor, continuous pressure tank reactor, and batch reactor for the non-isothermal condition. Okay. So before going to discuss about the reactor design, I will be discussing some basic concept that you all know that you all have studied in class 12 in thermodynamics. So first, try to understand one thing, and that's very important. So if there is a reaction in which reactant A is getting converted into product, right? So here, if rate constant of this reaction is A, and if I am assuming reaction is of the first order, right? So if I want to write rate of reaction in terms of RA, that is equals to KCA, right? Here, this will be question first. So I am going through some basic steps. Okay. So here you can see that rate is a function of rate of reaction. That is a function of uh, mm, K as well as concentration, right? So and rate constant of the reaction R is a function of temperature, right? K is function of temperature. So you can call it as RA, rate of reaction is function of temperature as well as function of concentration, right? Because rate constant here R K is rate constant. Here I am taking that is a irreversible first order reaction here. Irreversible first order reaction. So here we can say that this temperature is not going to be constant throughout the reaction. When the temperature is constant, then that reaction will be occurring at the isothermal condition. But if the temperature is not constant, then that is called as the non-isothermal condition. That you have to understand in this model, right? So just like if we talk about any reaction, just like a reaction is happening, this reaction A is getting converted into B is occurring in this continuous state tank reactor if this is CSTR, right? So if volume of this reactor is V and if volumetric flow is V naught and molar flow rate of reactant is FA naught and initial concentration is Ca naught, and here it is occurring at a steady state, that is V naught, and here it is also F naught, and here it is Cl. So can I write tau is equals to V by V naught, that is equals to Ca naught minus Ca upon minus of Ra, that is the design equation of continuous state tank reactor. So can I write tau is equals to Ca naught minus Ca, since the reaction is of the first order, so can I write Kca, and this Ca at the exit of the reactor, that is equals to Ca naught into 1 minus Xa, where Xa is our conversion in the reactor. So this is the basic design equation of the continuous state tank reactor. So here you can see now the value of rate constant is there. Okay. So if here in this reaction, if the reaction is occurring at constant temperature, that T, here it is constant, then this K is not going to be changed, right? Why? Because K is only function of temperature here. K is function of temperature. So if temperature is constant, temperature is constant, K will be also constant. So this condition will be the isothermal condition. But when we talk about the non-isothermal condition, then what will happen here? So first of all, if the reaction A is getting converted into product, right? If this is K, if this is N equals to 1. So first thing that we have to understand is heat of reaction, that is heat of reaction. Sometimes it is called as enthalpy of reaction. This is denoted by delta H of R. So that is equals to delta H of R, that is enthalpy of reaction, that is equals to enthalpy of product minus enthalpy of uh, a reactant, right? So that is equals to here delta H of B minus delta H of A, right? So if delta H of reaction is greater than 0, that is called as endothermic, and if delta H of reaction is less than 0, then that is called as the exothermic reaction. So this is the basic thing that we all know. And next thing is that here, that is a standard enthalpy. So a standard enthalpy of reaction is defined as at temperature is equals to 25 degrees centigrade temperature and pressure is equals to 1 bar. So this is called as delta H naught of R. I will later on I will be discussing about enthalpy of reaction at any particular temperature. So here it is called as the delta H naught R, that is enthalpy, standard enthalpy of a reaction. Now enthalpy of reaction, if we talk about, that is delta H of R. So enthalpy of reactions can be calculated in various ways, but here there are two most important ways for the GATE examination that we will be focusing here. That is enthalpy of formation in terms of, and second one is enthalpy of combustion. So last year in 2022, GATE has asked the question on the enthalpy of combustion 2022. GATE, they have asked to calculate the enthalpy of combustion, right? So the topic is really important because GATE panel is considering this topic, right? So you don't have to forget this thing. So first I am going to discuss enthalpy of formation. I will be denoting at delta H of F. So enthalpy of formation you can define as change in enthalpy during the reaction at constant pressure and temperature for the formation of 1 mole of substance from pure element, right? So if if we talk about oxygen, O2, so O2 is going to be formed, right? So there are various way of formations of O2. So the amount of enthalpy which is required for the formation of 1 mole of oxygen, then that enthalpy is called as the enthalpy of formation of oxygen molecule. Same time, delta H of carbon molecules, delta H of formation of nitrogen, same delta H of formation of CO2. So there are various ways. That is the experimental thing that you don't have to calculate theoretically. So all these things will be given in the problem. So you need to understand that is enthalpy of formation. Next thing here comes is a standard enthalpy of formation. A standard, so enthalpy of formation at pressure is equals to 1 bar, temperature is equals to 25 degree centigrade. Then this enthalpy of formation is called as the enthalpy of formation at a standard condition. Okay. Next very important thing is a standard enthalpy of formation of pure substance is assumed to be 0. So with respect to this standard enthalpy of pure substance, we used to calculate at a particular condition of temperature, right? That is called the standard enthalpy of formation. Next, coming to the second thing, that is enthalpy of combustion. So, enthalpy of combustion can be defined as the change in enthalpy for the combustion of 1 mole of substance. It's called the enthalpy of combustion. Okay, I'm writing the definition. Change in enthalpy for the combustion of 1 mole of substance. I'll be discussing everything. So, uh, let's try to understand with the help of one example. So, if a reaction is AA plus BB is getting converted into CC plus DD, where A and B is reactant, and C and D are product, and A, B, C, D are the respective stoichiometric coefficient of that particular reactant and product, right? So now, so there must be a enthalpy of formation of A, enthalpy of formation of B, enthalpy of formation of C, and enthalpy of formation of D, right? So if I talk about enthalpy of formation of A, so that is equals to delta H of F of A. If I talk about B, so I will be talking delta H of formation of B. If I talk about C, so it will delta H of formation of C. And if I talk about enthalpy of formation of D, so delta H of formation of D, right? So now, if enthalpy of formation data is given, so how can I calculate the enthalpy of reaction, right? So delta H of R, that is, if I am assuming this reaction is 1, enthalpy of reaction 1, that is equals to delta H summation of enthalpy of product of formation of product minus summation of enthalpy of formation of reactant, right? So can I write delta H of R, that is enthalpy of formation of product is C and D. So C multiplied with delta H of formation of C plus D multiplied with delta H of formation of D minus reactant is A and B. So can I write for the reactant A multiplied with delta H of formation of A minus B multiplied with delta H of formation of B, right? So you'll have to keep in your mind that all the units of enthalpy of formation of all the substance would be in the same unit, right? Otherwise, sometimes in the problem, you'll have to check. Otherwise, you'll do some mistakes while calculating. So check everyone's unit, right? So this is the enthalpy of reactions in terms of the enthalpy of formation, right? So now I am writing enthalpy of reactions in terms of enthalpy of combustion. Enthalpy of reaction in terms of combustion. So this is a little bit different. So if I talk about the reaction, same reaction, I am assuming AA plus BB is getting converted into CC plus DD, right? So if enthalpy of combustion data for A is given, that is equals to delta H of combustion of A, for B is given delta H of combustion of B, C is given delta H of combustion of C, and D is given delta H of combustion of D. All these things are given. So we can calculate delta H of reaction, that is equals to, here it will be called as enthalpy of reaction that is equals to summation of delta H of combustion of reactant minus summation of delta H of combustion of product. So try to remember these things. It's very important. Here the case is different as compared to the formations. So in the formation it was product minus reactant. So here it is a reactant and here it is product, right? So same way can I write delta H of reaction that is equals to A multiplied with delta H of combustion of A plus B multiplied with delta H of combustion of B minus C multiplied with delta H of combustion of C minus D multiplied with delta H of combustion of D, right? So again we'll have to focus the formula and the units of all the combustions data, right? And with a stoichiometry, because the stoichiometry is very important, otherwise you will do some mistake. So yeah, so these are the two very important formula. So which types of data is given in the problem, you can calculate this. So right now I have discussed about the enthalpy of combustion and enthalpy of formation. Now I am moving towards the heat capacity, okay, because uh, uh, let's try to see one examples here. If the reactions N2 plus 3H2 is given and forming 2NH3. For N2, if enthalpy of formation is H, for H2 enthalpy of formation is Y, and for NH3 enthalpy of formation is Z. So, can I write delta H of reaction that is equals to 2Z minus X minus 3Y. So, this is the way that you can calculate the enthalpy of formation, right? So, you'll have to focus on the unit as well. Now, coming to the enthalpy of reactions or enthalpy of reaction at any temperature. Okay, so at T naught that is equals to reference temperature. So enthalpy of reaction is given as delta H naught of R, right? And if Cp of reaction that is heat capacity is given, right? So you'll have to calculate uh, uh, delta H of reaction at any temperature T. How will we calculate? So delta H of reaction at any temperature T that is equals to delta H naught of reaction that is at T naught temperature plus T naught to T that is equal to delta Cp and dt. That's a very important formula. That is at any temperature, if you want to calculate the enthalpy of reaction, you can calculate, right? How? So just try to understand with the help of one example. If AA plus B of B is greater than equals to Cc plus dt. If delta H naught of enthalpy of reaction is given at temperature is equals to 298 Kelvin. So you'll have to calculate delta H naught, delta H of reaction at temperature T, right? So Cp of A is given, Cp of B will be given for the reactant, Cp of C will be given, and Cp of D will be given. So delta Cp you can write that is equal to C multiplied with Cp of C plus D multiplied with Cp of D minus A multiplied with Cp of A minus B multiplied with Cp of B, right? So this is delta Cp, and now further we can write delta H of reaction at any temperature that is equal to delta H naught of R plus integral T naught to T, that is C multiplied with Cp of C plus D multiplied with Cp of D minus A multiplied with Cp of A minus B multiplied with Cp of B, and that is dt, right? So sometimes you will see that Cp is also a function of temperature. So you'll have to substitute this here, and after that you will be calculating and will add with this standard enthalpy of reaction. This is called as enthalpy of reaction, and from there we can calculate enthalpy of reaction at any particular temperature, right? Next important thing that arises here, that is mean heat capacity. It's very important. Sometimes you will have to calculate mean capacity, that is Cp mean, because Cp may be function of alpha plus beta T plus gamma T square. If Cp is also varying, then in that condition you have to calculate Cp bar, that is mean heat capacity of that particular substance, and that is equals to T1 to T2 Cp dt and divided by T2 minus T1, right? T2 minus T1. Just like, try to understand, Cp is equals to 2 plus 3T, and if the reaction is T1 is given as just like 200 Kelvin and T2 is given as 400 Kelvin, right? So I mean T1 is given 298 Kelvin, just try to understand. So can I write Cp bar, that is equals to T1 to T2 Cp dt divided by T2 minus T1. So that will be equals to T1 to T2 2 plus 3T dt and divided by 400 minus 298. So now you will be able to integrate these things. We will substitute the limit from T1 to T2. After that, we will be able to calculate. One can calculate mean heat capacity of that particular substance, and after that, you'll substitute in this formula, and from there you can calculate this particular condition. Okay? Now, next thing is that uh, this was the parts of heat capacity. Now coming to the energy balance in continuous state tank reactor, that is the main important thing that you'll have to study. So from last 1 or 2 years, question has not been asked on the energy balance. So this year it's a very high probability that you'll see the question in the examination from this particular topic. So try to understand this. So this is our continuous state tank reactor. Here reactant will be entering and here product will be going out. Okay, so continuously reactant is coming and product is leaving. That's why it is known as the continuous state tank reactor, right? Now here what's happening here, try to understand. I am assuming that a reaction AA plus BB is getting converted into CC plus DD. This reaction is happening in this reactor. So first what will happen if we talk about uh, total overall material balance. So this continuous state tank reactor will be occurring at operating at a steady state. Why? So the volumetric flow rate here will be equals to volumetric flow rate here. That's why it will be occurring at a steady state. The volume of this reactor is V. Now, if this reaction is occurring, this reaction may be exothermic reaction or this reaction may be endothermic. Exothermic, endothermic. So reactor temperature will not be always constant, right? First thing. Second thing is that So if the reactor temperature is not constant, if reactor temperature is varying due to this reactions or some another things, right? So in that condition, you will have to focus on the energy balance, right? So how can we write the general energy balance equation? I'm not talking about only material balance because already you know the material balance in isothermal conditions. So here I'm discussing about the non-isothermal. So I will start with uh, a general energy balance equation. General energy balance equation. So here can I write energy in minus energy out, that is equals to d of E upon dt, that is energy accumulation, right? So if we talk about at a steady state, generally I am interested in calculating this value at a steady state. So our dE by dt, that will be equals to 0. d by dt will be equals to 0. So the continuous state tank reactor will be at a steady state. So energy in minus energy out, that should be equals to 0. That is equation first, right? So since this reactor, here you can see, here it is V naught, here it is V naught, right? So here I am assuming if nth ith component is entering here, right? And here the molar flow rate at the exit stream is Fi, right? Fi. And if enthalpy at entering is Hi naught, and if enthalpy at exit is Hi, I am assuming, right? And if the reactor volume is V, right? First, next thing is that due to isothermal and non-isothermal condition, maybe sometimes Q may be supplied or Q may be extracted here, right? I will let you know. So here energy in will be, can I write energy in will be sum of Fi naught Hi naught, and here minus energy out by mass flow, that is equal to sum of Fi Hi. So energy in by mass flow in, energy out by mass flow out, plus, can I write plus minus of Q? If heat is being added, that will be plus. If heat is being extracted from the system, minus Q, right? And minus W of shaft work, that is equals to 0. So that is shaft work, right? If heat is added, that is equals to plus Q. If heat is extracted, then it is will be minus Q, right? So this is the basic things of the continuous state tank reactor. So sometimes what we used to happen, if exothermic reaction is taking place inside the reactor, then in that condition what you'll have to do, you'll have to extract the heat. Otherwise, due to exothermic reaction of the nature, the reaction will go in the forward direction, right? So I'll let you know later for the reversible reaction condition. So what will happen there? But here at this particular moments, you'll have to understand this is the general basics equations of the energy balance equations of the continuous state tank reactor, right? So now we'll be focusing on Fi naught Hi naught. What is this thing? Since our reaction is AA plus BB is getting converted into CC plus DD, right? So what will happen here in this particular reactor? What will be happening? There will be Fa naught, Fb naught, Fc naught, Fd naught here, and here it will be Fa, Fb, Fc, and Fd, right? So First of all, I am trying to write the material balance, right? So if we talk about the material balance here, so here I am assuming FA naught, FB naught, FC naught is equals to 0, FD naught is equals to 0, and here it will be FA, FB, FC, FD. If our reaction is AA plus BB is getting converted into CC plus DD, and if XA is the conversion of limiting reagent, which is our A. Our limiting reagent is XA, so the conversion will depends upon the limiting reagent, right? So now what can I write? FA is equals to FA naught 1 minus XA, FB is equals to FB naught minus B upon A, FA naught XA, FC is equals to FC naught plus C upon A, FA naught XA, and we can write FD is equals to FD naught plus D upon FA naught XA, right? So this is the basics of material balance. So we have calculated FA, FB, FC and the FD. Now coming to the energy. So if we talk about Fi naught, Hi naught, so can I write Fa naught, Ha naught plus Fb naught, Hb naught plus Fc naught, Sc naught plus Fd naught, Hd naught, right? When I talk about FiHi, so can I write FaHa plus FbHb plus FcHc plus FdHd, right? Because second thing is that, so what will happen here? So summation of Fi naught, Hi naught minus summation of FiHi. What can I write here? That is equals to Fa naught, Ha naught plus Fb naught, Hb naught plus Fc naught, Sc naught plus Fd naught, Hd naught minus FaHa minus FbHb minus FcHc minus FdHd, right? So directly can I write Fa naught, here it will be equals to Ha naught minus Ha, and here we can substitute Fa is equals to Fa naught into 1 minus Xa, right? So now I can write here that is equals to plus Fb naught, Hb naught minus Hb plus Fc naught, Hc naught minus Hc plus Fd naught, Hd naught minus Hd minus Fa naught Xa. So can I write here C by A Hc plus D by A Hd minus B by A Hb minus Ha, right? So this particular thing can I write here like that, that is equal to summation of Fi naught, Hi naught minus Hi minus Fa naught Xa, and this is enthalpy of reaction. So can I write delta of H of R, right? So Fi naught Hi naught minus Hi minus Fa naught Xa, and that is delta H naught of R, right? So if we talk about total overall balance, so can I write that is equal to summation of Fi naught Hi naught minus Hi minus Fa naught Xa delta H of R, that is equals to 0, right? I think of, sorry, two more important thing was there, that is plus minus Q minus W is equal to 0. So case first, so here can I write here enthalpy of inlet condition, here exit enthalpy of reaction, and Fa naught is molar flow rate of the limiting reagent, right? And X is conversion of the limiting reagent, right? So here can I write better del Fi naught Hi naught minus Hi plus Fa naught Xa minus delta H of R plus minus Q minus W, that is equals to 0, right? So this is very important formula for the continuous stirred tank reactor, right? Now already I have told you if there is a variation in temperature and all, that already I have discussed you. So now if every species are going to enter at the same feed condition, right? So if I am simplifying this equation, this material balance equation, energy balance, with the help of one example here only. So here I am just taking example A is getting converted to B. Here rate constant is T. Rate here reaction is occurring at a temperature T inside, and here the reaction temperature inlet temperature is T naught, right? And if enthalpy of this reaction is delta H of R at temperature T is given, right? And uh, heat is supplying through it by a steam jacket, where U is overall heat transfer coefficient, A is area, and here the temperature of inlet of steam is Tc, right? So can I write Q is equals to UA Tc minus T, UA Tc minus T. Now, if in heat capacity of A is Cp of A and heat capacity of B is Cp of B, right? So here A is getting and if reactor volume is V, X is conversion, Ca node, Fa node, and V node, all these things are given, right? So can I write summation of Fi node, Hi node minus Hi, right? Plus Fa node Xa minus delta H of R, plus heat is being supplied, so plus UA Tc minus T, that is equals to 0, right? So can I write Hi naught is equals to Cp T naught minus T, right? And Hi is equals to Cp T minus T naught minus T reference I am assuming, and this is T minus T reference. So it will be equals to summation. Here Fi naught is only A, so here can I write Fa naught. So Hi naught is Cp T naught minus T reference, and again it will get common, so minus T plus T reference plus Fa naught Xa minus of delta H of R plus UA Tc minus T, that is equals to 0, right? So here what you can see that T reference and T reference will get cancelled out. So can I write directly summation Fa naught Cp T naught minus T plus Fa naught Xa minus delta H of R plus UA Tc minus T, that is equals to 0, right? Since only A is getting entered over here, because here we'll have to take summation of only inlet, right? So this now since only one component is there, so it will get cancelled out, summation will not be there. So next can I write, wait one second. So in the next slide can I write, so just wait one second, I'll have to add some slide. Yeah, so basically what I was trying to derive here is the formula was here Fa naught Cp of A, and that was T naught minus T plus minus delta H of R Fa naught Xa plus UA Tc minus T, that is equals to 0, right? So first case is that if Q is equals to 0, that is adiabatic condition, that UA Tc minus T will be 0 if no heat is supplying. So it will be equals to Fa naught Cp of A T naught minus T plus minus delta H of R Fa naught Xa, that is equals to 0. Why? Because I am not supplying any heat to this reactor, so I want to operate this reactor at the adiabatic condition, and I want to calculate this temperature T when the reactant inlet temperature is Ca, sorry, T naught. So I want to calculate this particular temperature or the reactor exit temperature, because the temperature here will be equal to the temperature here. So I am assuming this is adiabatic. So Q will be 0. I am also assuming W is also 0. Soft work is 0 for this particular condition. Otherwise, if something is given, soft work is given, then we'll have to subtract that soft work. So can I write here Fa naught Cp of A T naught minus T, that is equals to minus of delta H of R Fa naught Xa. So can I write T naught minus T, that is equals to sorry, minus delta H of R Fa naught Xa divided by Fa naught Cp of A. So can I write T is equals to T naught plus minus delta H of R Fa naught Xa upon Fa naught, and here it will be Cp of A. So the exit temperature from the continuous stir tank reactor CSTR T is equals to this, right? So this is very important formula. Now try to understand one thing. So we have got the formula T is equals to T naught plus minus delta H of R, that is Fa naught XA upon Fa naught Cp of A. If this reaction is only, A is getting converted into B. If delta H of reaction is also given. So if delta, will have to take two things, delta H apart. For exothermic reaction, it is negative. For endothermic reaction, it is positive. Okay. For exothermic reaction, it is negative, and for endothermic reaction, it is positive. So first, for exothermic reaction, when we talk about exothermic reaction, so T is equals to T naught. So in that condition, delta H naught of R is negative. So negative negative becomes positive. So plus delta H of R Fa naught XA upon Fa naught Cp of A. So if I am assuming this whole thing is sometimes A constant, so can I write T is equals to T naught plus A XA? T is equals to T naught plus A XA. So when we talk about the temperature profile of continuous state tank reactor when the reaction is exothermic, right? So try to understand the thing. Here it is a temperature and here it is conversion of reactant A. If reaction A is getting converted into B and if delta H naught of R is negative, this because this reaction is exothermic. So what will happen? The temperature profile is equals to T is equals to T naught plus A X A. This was the temperature profile. So it will like that. Here the intercept will be T naught and here that slope is equals to A and the value of A was equals to delta H of R Fa naught upon Fa naught and Cp of A. That is slope. Right? So this is for exothermic reaction. Now coming to the endothermic. Since the temperature profile was T is equals to T naught plus minus delta H of R Fa naught XA upon Fa naught Cp of A. Since case 2 is if A is getting converted into P, delta H of R is equals to positive. Positive means that is endothermic reaction. So for endothermic reaction, can I write T is equals to T naught minus delta H of R Fa naught Fa naught XA Fa naught XA upon Fa naught CPA, right? So if I am assuming this is A, so can I write T is equals to T naught minus AXA? So the slope of this particular curve is, if we draw the temperature profile for the endothermic reaction is continuous state tank reactor, that is temperature, and here it is XA. So it will start from T naught and it will decrease, it will be decreasing like that. So here the temperature will be T naught and that slope minus A, that is equals to minus of delta H of R Fa naught upon Fa naught Cp of A. So this is the two case that we can assume. So if sometimes if it has been asked in the problem that calculate the maximum temperature, so maximum temperature will be when the conversion will maximum. So XA is equals to 1, right? So this is the kind of thing that one can ask uh, in the numerical. So with that, I would like to end the meeting today. Actually, already I've discussed all the concepts regarding the continuous reactor tank reactor. So in the next lecture, I will be discussing about the energy balance in the plug flow reactor and energy balance in the batch reactor. Okay. Thank you and all the best.